Okay, let's get started. Project number 5 is due 1 week from today at class time. And all of you should have gotten your test number 2 back. Let's briefly talk about some aspects of test number 2. First of all, it's kind of small, but this is the listserv posting. The grades were very similar to last time. The meeting was 84% for this test, and last time was 83%. So,
That's actually the first test.
oh, sorry. I had to look back at my my notes. So last time was 84%. This time was 83%. Sorry about that. Let's talk about just a few of the problems. Some commonly missed problems. Number 1, A and B, unfortunately. Got to remember resampling the null hypothesis. Big things from Chapter 4 that you needed to get out of it was to resample the null hypothesis. Now, obviously, if you didn't resample the null hypothesis, you didn't lose all 8 points on A or all 12 points on B, but obviously you did lose some points. Also, hopefully, and perhaps this scared some of you when you were taking the test, that when you got to Part C, I said, well, you should be rejecting the null hypothesis. And if you didn't resample the null hypothesis, well, you didn't reject the null hypothesis. So it should have been a tip-off that something was going on wrong. Number 2, I think most people did a very good job on that. I think very few people ever miss, or very few people missed these points. So that was good. Number 3, now ideally what I would like to do for Part B was I want you to calculate the BCA interval, let's say by hand without the boot.ci function, but it's quite hard for me to do that exactly. So I just thought I'd put this on there and just have you go a little bit one step further in terms of tell me which ordered T-star value was actually picked. Some of you actually did try to find A, the deceleration constant, and W, the bias correction, and then actually do all the by-hand calculations. That was the long way to do it. The easiest way overall, though, that wasn't smart. Second. Easiest way was to realize that actually what's being returned to you in the BCA component of boot.ci are the values that you need. That was the easiest way. Some of you also said, well, what I can do is just simply search for this point 3756 in an ordered set of my T stars and figure it out that way. And that took a little bit more time. But still, the easiest way was to look at the return object from boot.ci. But this gives you an example, too, that sometimes you need to think about what's the easiest way to do a problem, because obviously calculating A, calculating W, finding the code to do that, that's the long way. It's going to take you some time. And when you have a limited amount of time on a test, that can hurt you. Okay. Let's see now. Part D. This was just kind of an extension to the one that we talked about in class. I didn't want to give you exactly the same one, where we have this semi-parametric model, but now instead of having additive structure to it, we have a multiplicative structure to it. Well, what will be the residuals in that case? How to then do the resampling. You know, most of you got this part right, correct here. A lot of you, though, missed this part, how to get the residuals, and you're actually using the residuals from the example that was in class. There is a typo on 4B in terms of the answer key. For some reason, this equation was left off. So you might want to make that adjustment. That will make it a little bit more, make it more sense. But this was just something that we talked about in class regarding why we were doing what we were doing for project number 3. And lastly, I hope in part C, 4C, most of you left off the need to be symmetric about 0 for the statistic. And so originally I didn't have this in my answer key, but I thought I put this in here that I think really drives home the point why you need a symmetric about 0 statistic rather than just a symmetric statistic itself. Anyway, just some things I wanted to discuss that were most commonly missed. Are there any questions about the exam? Okay. So last time we talked about one way to do resampling with respect to a regression model. This is on page 622. And we talked about what's called a model-based method to do the resampling. Let's review that because we will use it later today. Model-based resampling. And let's say we only have one explanatory variable, one response variable. The first thing that you need to do is come up with your estimated model. So y hat, or what our book likes to call instead mu hat, is equal to beta hat 0 plus beta hat 1 times n. So just estimate your model. And then, so let's call that step 1. In step 2, we need to form some kind of residuals. And so we can form our regular old residual. Let's call it E sub j, where we take y sub j minus mu hat sub j. Then we can also talk about a modified residual, which now incorporates part of the hat matrix. And the reason why we do that is so that we get a residual that has the same variance. And we go one step further and we form rj minus r bar. And the reason being is because the rj's don't have to meet exactly equal. And this is what we resample. These rj minus r bar for j equal 1 to n. Or that's where we're taking our resamples from. And then to find y hat j, we do like what we did with semi-parametric model back in chapter 3. We take y hat, I'm sorry, that's not y hat. Let me get my eraser out. Y star sub j is equal to mu hat j plus epsilon j star, or equivalently we can say beta hat 0 beta hat 1 times xj plus epsilon j star, where these epsilon j's are resampled from the rj minus r bars. So the reason why this is called model-based resampling is because we're assuming a particular model structure to our data still when we're forming our resamples. So while our book kind of refers to this still as a non-parametric resampling approach, I guess I think it more as a semi-parametric. Okay, so that's model-based resampling. The second way that we're going to talk about taking resamples is to do what's called case-based resampling. This is an easier way to take the resamples, but there's advantages and disadvantages to it, just like there was with model-based resampling. And simply with case-based resampling, all we do is resample from our XY pairs. That's it. And so essentially what you're doing is you're assuming that you have some kind of bivariate distribution for X and Y. And so we're going to resample from the X and Y pairs that are actually observed. Obviously, this is easier. One of the advantages of doing this is because one of the advantages of doing this is that it makes less assumptions. We're not necessarily making that model assumption that we were doing with model-based resampling, which one of the big parts of that then is that you have constant variance. And we had to do some stuff so that we get pretty much, we're resampling something that has a constant variance. So we're not making that assumption. Big deal, Obviously, though, you do have constant variance, or approximately constant variance, then the model-based resampling might be better to do. But one disadvantage of case-based resampling is that resampling these cases, these XY pairs, causes what are often referred to as different designs for each resampled data set. What that basically means is that you will have different X's in each resampled data set that different possibly from what was actually observed. Now, a potential problem where this can cause is that let's say that I think we kind of discussed this before, let's say that I had all my X's in my data set were between 0 and 4. Well, since I'm resampling XY pairs, now I could get maybe in a particular resample that I have something like this, where my X stars are no longer within my original range of my X's. And where could that potentially hurt you is that, if I was finding a confidence interval for the expected value of Y, let's say at X equals 4, well, guess what? Some of my resamples don't go all the way to 4. So that can be a potential problem here. A disadvantage to do this compared to model-based resampling, where you always have exactly the same X's. In other words, you have the same design. However, then the authors of our book go on to say, well, this variation that we see in these X stars will cause some variation in information that you have. But fortunately, this is often unimportant in moderately large data sets, which you can think about, simply if you have a large data set, if you lose one X that was originally in the original sample, that's probably not going to be that big of a deal. So let's look at an example. This is with the mammals data. And Elizabeth told me before class, maybe some of you heard, that the mammals data is actually in the mass package. And you can look it up and find out exactly what animals these mammals were. And also the scale that the data was measured. Anyway, so I have to now construct a calc.t-like functions, what we've done before. So I'm going to have calc.t.cases, just to differentiate it from what we had earlier. I'm going to pass in my data and my indices just like usual. But what I'm going to pass in here is my actual data set. Back when we were doing model-based resampling, we would pass in these residuals, and we had a vector of these modified residuals, mean-adjusted modified residuals. We had a vector of them. Here I have an actual data frame. So because of that, then, when I do my usual first step in a calc.t function, I say data bracket I comma in bracket, because now I want to resample rows of my data frame. So then simply You estimate your model like you would normally with the LM function. You summarize the model fit like usual, and pass back then my beta hat 0, beta hat 1, and my square root geometry. So that then when I actually test this out on the actual observed data, notice what I get here. I get the actual beta hat 0, beta hat 1, and square root of MSE. Remember, with model-based resampling, we didn't get exactly the same value. It was always close, but it wasn't exactly the same. So to do the resampling, it's not that difficult. We just use the boot function like what we would normally. Notice I again have the entire data frame there. So put the results in boot.res.cases, and this is the output that we get. Let me look at my notes. Okay. So, we have the usual stuff here. For example, this in purple here represents the square root estimated variance star of beta hat 1 star. Here is then also the estimated bias for beta 1, which is estimated bias. And what I try to do is then put this information into a table that corresponds to something that's that's in the book, table 6.1. Maybe I'll do split screen here. And just kind of helps summarize everything. So in the book, they have a table that looks like this. Change one thing here. So they have a column that's called theoretical. And what this represents is for beta hat 0 and beta hat 1 itself. Notice I'm not saying stars. This is what the bias will be. Of course, the least squares estimates are bias estimators. And also what they put in the table 2 is the square root estimated variance of beta hat 0. So this is an estimated, it's a standard error. But it's not the square root of the true variance. It's called theoretical. So this was just obtained from just the original output that we had last time using the LM function. So that's all I did. Went into the summary of the model fit and grabbed these out there. Okay. Now through resampling cases, then this is what the corresponding estimates of basically, we say these values are. Notice how I've color-coded stuff corresponding to what was in the output. Make sure you put that on my teaching evaluations, and I make it so easy for you to find stuff. I color-code it. So we can see here, and this is nice, that these biases are about 0. Okay. Also, the standard errors, they're close. They're not exactly the same. We should expect them to be exactly the same, but they are in the ballpark. Then lastly, the authors also have a column called Robust Theoretical. And what that basically means is that they use the non-parametric delta method to do their calculations. This is just directly from the book using the actual empirical influence values. What I show then, starting on the very bottom, page 624, is how we could get these values estimated using the jackknife or the regression method. And it's pretty much similar to what we've seen before, but I think this is a good review. So first of all, I used the regression method. So I've saved my results in boot.res.cases. I used the old ENP-INF function. And I want to estimate, basically, LJ for beta hat 0. So I'm going to use an argument. I don't know if we've seen this before. Index. Index equals 1 because in my calc.t function, the first element that was returned was the beta hat 0. I do something similar now for the LJ for beta hat 1. We're now exactly the same so far, but index equal 2. Because that was the second element that's returned by calc.t. With respect to the jackknife, then, maybe I should put a hat on top of these L's. With respect to the jackknife, I do exactly the same kind of thing. Notice I say S type equal I, type equal jack, and I use the actual calc.t function. So that then using var.linear, you can find your variances, and here are then the corresponding square roots of those variances. Let me do a split screen again here. And again, they use the authors use the actual empirical influence values. I'm estimating them, and we can see we're getting just about the same values, which we would expect. Any questions? Okay, also, I just try to reproduce figure 6.3 in the book. It's just to examine the distribution for these beta hats and beta hat stars, that is. I mean, we know that beta hat itself should have a normal distribution. We can kind of check to see if this is actually holding true by looking at the Bootstrap results for the beta hat stars. So I use the usual QQ plots and also the usual QQ plots just to examine this. I use this for beta hat 0 star and beta hat 1 star, and it looks pretty good. Pretty good. The authors of our book do something a little bit different. It's just the same basic idea. If you want, you can take a look at what they do. I have actually included their code here and also the plots. Okay, that takes us to page 629. So now we're going to look at hypothesis tests with respect to the Bootstrap and the regression model. As we saw in Chapter 4, it's not necessarily a straightforward, simple thing always to figure out how do you take the resamples. Do you need to take the resamples under the null hypothesis? And the regression model makes it sometimes, we say, even more difficult to figure this out. I think especially once we get to multiple linear regression it does. So what I like to do is, the old hypothesis test of beta 1 is equal to 0 versus beta 1 does not equal 0. Now in a simple linear regression model, if you remember from your regression days, this is equivalent to testing the correlation coefficient. The test is exactly the same, with exactly the same result. Okay? This was, and the reason I bring this up is because back in Chapter 4, there was actually an example in the book that looked at how could you do permutation tests and also Bootstrap tests for a correlation coefficient. So, let's talk about permutation tests here. How would you take the resamples? I think it's easier to think in context of the correlation coefficient. You're going to do a test for that. Resample.
You can think about them as columns and rows, I guess.
So we got X's and Y's. So what we could do is resample from the X's independently of resampling from the Y's. Notice how this is very similar to what we were doing with our contingency table problems. Basically, it's the same idea because you are testing independence. We're testing independence here, but we just have different data. We don't have row numbers and column numbers. So now remember also in this case, since we're doing a permutation test, we are actually resampling without replacement. So essentially what we could do is just simply resample the X's only, keep the Y's where they are. Or resample the Y's only, and keep the x's really high. So just to make sure it's clear, let's say that we have an x is of 1, 2, 3, and a y of, let's say y1, y2, y3, okay? Now, for the permutation test, one possible resample, a y star, could be y3, y2, and y1 in that order. And so what we could do then is now estimate a regression model using x and y star for the first resample. So what are the sufficient statistics? Well, basically it's just the ordering of the x's and the y's. And what is the p-value? What will be the p-value here? How would we calculate it? What am I calculating for every resample? Yeah, let's say that we're calculating beta hat 1 star for every single resample. And so we're going to get a bunch of beta hat 1 stars. And that's essentially going to replace, let's say, a normal distribution for beta hat 1 that you would normally use. So, and the p-value could be something like this. 2 times the minimum of 1 plus beta hat 1 stars, or the number of beta hat 1 stars that are greater than or equal to beta hat 1, because you're looking at the relative position of beta 1, beta hat 1, with respect to this distribution that is formed under the null hypothesis over 1 plus r, and then also the exact same thing on over here, but now you put a less than. So is everyone comfortable with that? Okay. Well, how can we do this with the Bootstrap? How about we do case-based resampling? Now, when we're not resampling under null hypothesis, what we're doing is resampling XY pairs. Now, when we need to resample under the null hypothesis, now we're going to resample from the X's and also resample from the Y's independently of one another, because it's under null hypothesis, and then put them back together. That's how you would do it. Essentially, it's the exact same thing as with the permutation test, except for now we're, resampling with replacement. And we're actually resampling both the X's and the Y's.
Do you have to resample both the X's?
Yeah.
So unlike the permutation, we can get away with just doing one.
Yeah. I mean, when you're doing, since we're doing without replacement,
right,
with the permutation test,
really
all you're doing is just mixing things up more.
Right.
So, and maybe it's also easier to see, too, why this is still called case-based resampling. If you kind of jump ahead to think about multiple regression, we'll get to multiple regression probably next time. And let's say a simple case where we have y, x1, and x2. So we simply have two explanatory variables. How would you do the resampling here under the null hypothesis? You would resample x1, x2 pairs. You're keeping them together because it's a case. And resample those independently of your ones. Hopefully you can see my vectors and matrices of data as I'm demonstrating with my hands. I like to talk with my hands. I've gotten in trouble with my wife from talking with my hands, especially when I'm driving. I have scared her a few times. Anyway, so once we take then these resamples under the null hypothesis, we estimate the full model. so that we get our beta hat 1 star, form the distribution of the beta hat 1 stars that plays the same role as what we had above when we were doing the permutation test, and we form our p-value the same. Okay, well now what about model-based resampling? Well, what's our model if the null hypothesis is true? That's where you start. Well, where we saw beta 1 before, now we replace it with a 0. So our model under the null hypothesis is just simply yj is equal to beta 0 plus epsilon j. That's it. So I'm going to need to, first of all, estimate my model under the null hypothesis. So I want to get, you could say, y hat, let's say j is equal to beta hat 0. Now notice I have a j on y, but I have no j's on the right-hand side. So, what is my estimate of y, or I guess you could say mu, for every single observation? Yeah, just y bar. So, if maybe you've never even tried this before, estimate a model without any explanatory variables. Your beta hat 0 ends up being y bar. And that makes sense because then beta hat 0 is equal to, let's say, mu hat for us. And how would you estimate mu if you didn't have any explanatory variables? Well, use the mean. So then, once I have my estimated model under the null hypothesis with my observed data, then I need to use that information to do my to form my y stars. Again, remember how we would do this normally when we're just taking resamples in the normal way. We estimate our mu hat. We use that to find our residuals, our modified residuals, and our mean adjusted modified residuals. And finally, we form yj star by taking this mu hat under our model plus the epsilon j stars, which are resampled from these guys. We do exactly the same thing here, except for we replace this mu hat j with its estimate under the null hypothesis. These epsilon j stars come from the model that now had the uj under the null hypothesis in it. So here we go. In the end, what ends up happening is yj star ends up being y bar plus these epsilon j stars. Now, there are some simplifications that occur in a very simple model like this in terms of what these epsilon j stars can be. So, rj is equal to will be yj minus y bar over the square root of 1 minus hj. This hj, you can prove this to yourself. I discuss this a little bit in the notes later. Ends up being just simply 1 over 8. Just the hat matrix diagonal diagram. So now that once I have these yj stars, then I estimate my full model. So I have yj star 1 and x1. yj star 2, x2. I estimate the full model so I get my beta hat stars. Again, these beta hat stars come from under the null hypothesis. I can find my p-value in the usual way then. Okay. So, sometimes, we'll see a case of this later on today, sometimes you want to do a test for beta 1 is equal to some constant that's not necessarily equal to 0. It's called beta 1, 0. How would you do the test in this case? It follows the same things that we just have done, but now you have to make some adjustments. So notice that here's what my model would look like under the null hypothesis. What I could do is rewrite the model like this. So that now I have the beta 1, 0 times xj on the left-hand side. And in fact, we can change our response variable to be yj minus beta 1, 0 times xj. So it's just like an adjusted response. Because now you're not estimating the beta 1 anymore. It's a constant. X is a constant, let's say. Model-based result. And you can then proceed with this adjusted y in a very similar manner to what we did before. You'll see an example coming up. Our authors talk about Bootstrap pivot tests. What this basically means is using a studentized value. We talk about the case where you don't have to resample under the null hypothesis. You're not responsible for it. You're welcome to read it if you want. But if we were to now resample under the null hypothesis and we want to find a studentized value, you remember why we often like to do that. Often we get a better statistic to work with. We can do this, we can find a studentized value with either the case-based or model-based resampling approach. So what we would do is form a Z0 star, let's say, that contains your beta hat 1 stars. It came about, again, assuming the null hypothesis is true, minus some hypothesized value of your beta 1. You've got to be careful about what that actually should be. And I'll discuss that in our example. Divided by what is essentially, again, var hat star beta hat 1 star. That might not be okay, but that, sorry. The square root of the estimated variance of beta hat 1 star. Meaning you could use, let's say, the non-parametric delta methods, estimates, to estimate the variance. You could do it as a double bootstrap as well to get that the needed variance estimate. And then once you have that Z0 star, then again, all this is doing is trying to replace a regular old normal distribution, or let's say even t distribution. So you actually use a t distribution. Replace that usual parametric distribution now with this basically, think of the histogram of the z stars. And then you can calculate, let's say, your observed value of Z0 from your observed data, and then calculate a p-value. You could do it one of the two different ways that we've discussed. Again, the z star distribution should be, if normality worked out and stuff like that, will be symmetric about 0. I still prefer this one, but you'll often see people use this one. Okay, so let's take a look at an example. This uses the returns data. That's a data set that's involves a data set that's in the boot package. It involves something called a beta coefficient. Has anybody ever heard of a beta coefficient before in finance? Okay. This is often, for those who teach Stat 218, I know when I would teach a similar course like that when I was a grad student, in a few times I've taught a similar course like that when I've been in a professor now. This provides a nice little regression example to give to students, because it's simple linear regression and it involves relatively simple data that's easy to get. So what a beta coefficient is in finance and investments, it's a measure of the stock's relative risk to that of the average stock. And often investors want to know how risky is a stock compared to, let's say, an average stock, where the average stock is often thought of as some kind of index, maybe S&P 500 index, for example. Am I taking on more risk than if I would just simply, let's say, put my money into a S&P 500 index mutual fund, or am I taking on less risk? And in statistical terms, then, what the beta coefficient simply is beta 1 in a simple linear regression model, where your explanatory variable is the average stock's rate of return, and the response variable is the stock of interest, their rate of return. That's it. Very simple. And this stuff is quoted in many places. So, for example, before class, I was taking a look at Berkshire Hathaway, Class A, $130,000 per share, and this is just from Google's Google Finance. And you can see over here, I already have it highlighted, the beta coefficient is 0.49. To show that this stuff's out there. And it gives you a little bit of information about what a beta coefficient is. We can look at ConAgra. So we'll stay in Nebraska here. It has a beta coefficient of 0.69. And we'll look at Apple as well. It has a beta coefficient of 1.21. Okay. Now, without looking at my notes, which of these stocks, based upon this beta coefficient, do you think is more risky, as measured by the beta coefficients? Apple. Why?
Higher. Say, like a 1-to-1 would be, it was the same risk, and so if it's higher than that, it's higher risk.
Exactly. So what we're looking at often is how close is this, what essentially is a beta hat 1. How close is this beta hat 1 to 1? If it was equal to 1, basically it says that this stock has the same risk as the index. If it's less than 1, it has less risk. And you can think of it in terms of, just a regular old scatter plot. So what I'm going to plot here, for example, is let's say X, we could call that S&P 500 index. This is the returns, maybe daily returns. If you don't understand what daily returns are, I'll explain it, what it is in just a second. And then we have Y here, which, draw a Y. We have Y here, which is, let's say, Berk A. And, if you see something like this, and you fit a regression model to it, and let's say that this is all on the same exact scale, so here's one, or 0.01, 0.01. So the X and Y axis are exactly the same scale, and this would mean that I would have a beta hat 1 equal to 1. Okay? If instead, and you see something more like this for your model, then beta hat 1 is less than 1. So what that's saying is that as X is increasing or decreasing, Y is increasing or decreasing at a slower rate. And perhaps, since I'm just going to do this on the fly here, maybe I should extend it over here to demonstrate that you have to worry about negative returns as well. So while you might be thinking, well, why is Apple a more risky stock? Because it's just been going up, 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 up. Well, watch out, it might go down, 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 down. It's going up at a faster rate than, let's say, the S&P 500, which is good, if you're investing in it, but it could go down too. It could have bigger fluctuations than the S&P 500 index. That's why I like an investment like Berkshire Hathaway, because it's a little bit less risky. I happen to be a shareholder for Berkshire Hathaway, but I do not own any of the Berkshire Hathaway A shares. I have the B shares, and I only bought. I bought. I don't know how much you follow Berkshire Hathaway, but Berkshire B for a long time was. It was, I think, it was originally like the 1990s was meant to be like 1/100th of a Berkshire A, something like that, and I bought like one share a few years ago, just so I could go to the Berkshire Hathaway meetings. Now it's now they've split the stock. It was a 50-to-1 split, so now it's like trading at 80.
Is it that high? I was thinking it was like a 35 or 40 or something.
I think it's about 87, 88, like.
Plug it in and get it.
What's that?
Put it in and get it.
What do you mean? Oh, yeah.
Change your
Yeah,
stocks and it'll be.
I forgot that we live in a world where you get instant answers to your questions. Oh, darn, it's down today. Well, at least it's down from the last time I looked at it. It's 86.79. Anyway.
And then ever so slightly higher beta.
Yeah, that's interesting. Well, you know, I mean,
It probably
while they're
gets
kind
traded
of,
up a lot more too.
yeah, it's traded a lot more. So while, you know, it purposely was set at a certain rate, it's not exactly the same. But it's going to be very similar because I think Buffett said that you can always trade, you know, an A share for a certain number of B shares. So that's why they will always be very, very similar. But if you're looking for something to do on a Saturday in early April, it's fun to attend those meetings amongst 30-some other thousand people down the Quest or Central. Anyway, though, so I've been talking about these returns, and you know, if you're not familiar with investments, you might not totally understand, but it's very, very simple. Basically, suppose you have, let's say, the stock price at the end of trading today, and you also have the stock price at the very beginning of trading today. So let's let the end of trading be my new stock price, previous stock price be the beginning of today. And so if you take the end minus the beginning divided by the beginning, you get the return of a stock for that particular day. So if you had a value of 0.1, that means your stock went up 10%. And so what's done with these beta coefficients is that you get maybe these daily returns for both the S&P 500 index, meaning the daily change, and also then the returns actually for a stock, and that's your data. That's what you fit a regression model to. You know, unfortunately, just going back here to what we were seeing here, you know, unfortunately, it doesn't give me any information here on exactly, you know, how long in the past it's going to find this beta coefficient. It would be interesting to see exactly what they do. It doesn't tell me also if it's based on daily returns or monthly returns, weekly returns. It doesn't tell me. Okay, so the reason why I gave you that little bit of background here is because we're going to look at estimating beta coefficients for this data set that is in the boot package. It's for the Acme company. And so they have these actually monthly returns. So the first month it went up 3%. The next month, ooh, not good, went down 16%, and so on. What's that?
Acme not doing well.
No. And then we have a variable called market. And I don't believe they're using like an S&P 500 index or maybe Dow Jones Industrial Average Index or Russell Index. I believe what they're doing is using probably an index measuring returns that you can get from a U.S. Treasury, because they refer to this market as a riskless rate, and often people refer to as a riskless investment as investing in U.S. Treasuries. That would be true unless our government goes bankrupt. Hopefully that doesn't happen. We don't go off the fiscal cliff. Anyway, we don't talk about politics here. What we need to do in this particular case is to do the following hypothesis test. You can think of an investor wanting to do something like this. You know, an average everyday investor, you know, they go to, you know, like a Google Finance, they just look at the point estimate, the beta hat 1. But, you know, for those of us who are more sophisticated in terms of our statistical knowledge, of course, we would be interested in doing a hypothesis test such as this. So let's look at how we can do it. So this is what my data looks like. We're going to find my sample size. I believe it is 60, so 5 years worth of data. I estimate just my regular old model, and unfortunately I'm using bad coding here. I forgot to put the actual argument name. I would say formula equal Acme tilde market. I summarize the fit and put the summary into something called sum.fit, and then I look at sum.fit. So we can see that my beta hat 1 in this particular case is 1.13. So it's a little bit more riskier than the market index. Interestingly, I don't usually see, at least what I know of finance, I don't usually see people examine R squares at all, but those are the R squares. So you can see it's not perfectly correlated. Let's see here. And then we could do our own regular old hypothesis tests for beta 1 equal to 1 or beta 1 greater than 1. And the way that we would do that is we form a test statistic called Z0. Actually, let me just write it out to make sure it's clear. Z0 is equal to beta hat 1 minus 1 divided by the square root of the estimated variance of beta hat 1. So that estimated variance, or the standard error itself, so including the square root, is 0.229. Beta hat 1 is 1.13. So let's actually get the test statistic itself. Let's go ahead and do this. So the test statistic is 0.57, or we'll call it 0.58. Just be careful here. Of course, you don't want to look at the stuff that's in the summary output, because that's testing whether or not beta 1 is equal to 0 or not.
Is there any way to modify that?
I don't know of a way. I mean, obviously, it's not too difficult.
Yeah.
And normally you would do a regular old t-distribution approximation, and with n-2 degrees of freedom, you get a p-value of 0.28. This is a right-tailed test. If I use a normal approximation that they do in the book, you get 0.2813. So you can see, for those who teach Stat 218, how this is just a nice, simple linear regression example that you could do. Let's look at how we could do this now with the Bootstrap. Or before we get to that, we can look at some stuff that the authors did in Figure 6.4 of our book, where they actually found the modified residuals, and also they did a scatter plot of the data along with a plot of the modified residuals, and this is what they get. So what do you think here? Do we have any maybe potential problems with our model or violations of our model? Well, what they're concerned about in the book, so notice how the variability here is less than the variability here. Notice on this scale here, this is absolute value of R. So it's a little bit different from how you normally would plot this, where you would just plot, let's say, R or the residuals themselves. They actually plot the absolute value of R. And you can see, again, some extra variability for larger X. So they're a little bit concerned about non-constant variance. So, you should think about in terms of, which resampling approach might be best. Maybe case-based resampling would be better because it doesn't make the assumption that a model-based resampling would with our particular model. I have to admit, though, that while the book is concerned about non-constant variance, I have a little bit of a concern, but not necessarily a strong concern. And the reason being, this is what I tell my students, my teacher static semi-class, is that you can't get too picky. Okay? So, what I say is, if you could just, let's say, cover up a few observations, very, very few observations, so you can't see them anymore, would you still make the same conclusion about non-constant variance? Maybe not. You have to judge also, with respect to, how many observations you have certain spots. So if you're saying here, oh, well, look, you still have very little variability down there. Well, I only have 2 observations. You can't say, oh, I have less variability here and a lot more variability here. You can't say that. You know, if you have more observations here, you might have more variability. You might be able to see it. But if I only have 2 observations, it's not going to necessarily hurt you. So I actually then, before class, because I was curious, I actually performed 2 particular tests for constant error variance. I think probably all of you have heard of a Levine's test. And if you're interested, let me move this one too. If you're interested in knowing how to do this, take a look at my study notes. But here in the CAR package, this stands for Companion to Applied Regression. It's a book on how to do regression analysis in R, and also how to do generalized linear models in R. I took my categorical class. I might have mentioned this book too. And you just basically have to divide your data into 2 groups based upon median, and then do Levine's tests, which is basically very similar to a paired t-test, or 2 single t-tests. And to get a p-value of 0.09, so there's marginal evidence of non-constant variance. There's another test, and then you heard of this particular test, I guess it's pronounced Boris-Pagan test. I call it the BP. It also gives you a marginally significant. So, it's kind of like what we were seeing in the plot. That, yeah, maybe there's a problem, but it's not necessarily definite from there. Okay. Well, here's another potential problem that the authors don't bring up, and most people who, at least in my experience in investments and finance, I haven't seen people bring up much either, is that do we have to worry? Do we need to worry about a dependent error terms here? Now remember, one of the typical assumptions that you have with a regression model is you have independent error terms. Do you think we need to worry about this here? Not looking at my notes.
Are going up so we keep going up.
Well, we're measuring stuff over time. That's the key. If we're measuring stuff over time, we might be worried. Well, how can we do that? Well, we can apply stuff from time series analysis to investigate this further. So what we can do is just a simple plot of our data over time. Let's see if we have potential patterns. And we can also look at what's called an autocorrelation function. And if you've never heard of an autocorrelation function, what it basically is this, where let's say I have, I'm just using this as a symbol. Let's say I have some data, we'll call it y, and I have y measured at time t. And if I look at the correlation between y at time t versus y at time t minus 1, so in other words, you can think of, here's y2, here's y1, y3, y2, in terms of forming a data set, I'm going to find the actual correlation between these 2 values. Okay? This will give me my first autocorrelation at time point at what's often referred to as lag 1. You can also then do yt minus 2, autocorrelation at lag 2. And so I did some plots. Here's my residuals over time, and as what often occurs, it's kind of hard to see necessarily a dependent structure unless it was quite obvious. And then on the right-hand side, I do a plot of these autocorrelations. I guess I should say the reason why it's called autocorrelation, because you find correlation on the variable itself, so autocorrelation. And so at what's called lag 1, this would be the correlation between yt and yt minus 1. We have a negative correlation of about negative 0.2, and the actual value in there, negative 0.279. For a lag 2, we have a correlation of negative 0.058, and so on. These dotted lines here are drawn at the if an autocorrelation is inside these bounds, that says that it would be what you would expect if the true correlation, let's say the population correlation, was actually equal to 0. If you have an autocorrelation that ends up being outside those bounds, it says, uh-oh, now you might have a true autocorrelation that's not equal to 0. And so, and this is using 95% confidence. And so what we can see here, we have two places where we might have a little bit of evidence. But you also got to remember, if you look throughout here, we're doing essentially 17 hypothesis tests. So, we're not necessarily accounting for a family-wise error range. Now you might be thinking, well, what about this one right here? That's 1. Well, that's an autocorrelation. That's at lag 0. So it's the correlation between YT and YT, which will always be 1. I don't know why R puts that there, but it does. So anyway, so we might have some problems. We're not necessarily totally confident that we have some problems with this dependence. What could be done? Chapter 8 of our book talks about time series analysis and how to handle when you do have this correlation structure. Where you don't have time to get into in this course. But there's a number of ways to handle it. In particular, one's called a block bootstrap, where what you might do is, let's say, resample blocks of your data. So, for example, I might, instead of sampling, let's say I have a simple data set of just Y's, I might resample a block of size 5 always of my data. So I might resample Y1 through Y5, or maybe I'll resample Y2 through Y6. And the reason why you do that is it helps preserve the correlation structure versus resampling the Y's in the data. There's other resampling techniques too. That's just one that's common. Also, what you could do is maybe use a regression model that allows for autocorrelated error terms as well. That's a possibility. Our authors choose to ignore the autocorrelation, and I'm going to do the same thing as they do so I can reproduce their example. Okay. So finally, we get to the actual bootstrap part. So we're going to do case-based resampling first. The first thing that we need to do is we need to take our resamples under the null hypothesis. When our null hypothesis beta 1 is equal to 0, it was quite simple. All we did is we resample from the y's independently of resampling from the x's, and we put them all back together. Now, what do we do when beta 1 is equal to 1? We adjust our data so that we have, you could say, a beta 1 equal to 0 again. How? Take y tilde be our adjusted values. Take yj minus beta 1, hypothesized value of it, times xj. So that now, here's my adjusted value. And if I were to estimate, perhaps I shouldn't do this, but I'm going to anyway. Now, essentially, if I have this modified y, now there's my modified model, and I could do a hypothesis test for beta 1 tilde is equal to 0 or not. Okay? And in that case, we know how to take our resamples. We independently resample from the y tildes, independently resample from the x's, put them together. And that's what we do. Now, to get this actually done with the boot function is not necessarily the easiest thing. And, this comes back to, like chapter 4, where, it's not always easy to, do the bootstrap with the boot function when you have to modify your data in some way to resample the null hypothesis. But this is how I did it. I'm going to jump over here to Tim. First thing I need to do, I need to get my data into a particular format. I'm going to use a format that we first saw in Chapter 3, where I'm going to create a data frame. I'm going to put all my x's, the market values, market index values, into the data frame, and also label it with the value, or the value x. I'm going to combine that with then another data frame that has my y tildes in it, and simply label it as y tilde. I R bind them together, so I have my x's on top of my y tildes, and this is what it looks like. Okay. Now once I have that then, let's form my calc.t function. So calc.t.case is function, data, and my index. When I do my resampling, I'm going to use stratified resampling. I'm going to tell R to basically, remember there are 60 observations, resample from the first 60 in this restructured data set, and then resample from the next 60 in this restructured data set. So similar to what we saw in Chapter 3 then, I get my resampled data, I pull out my x, I pull out my y, I estimate my model, summarize the model, return my beta hat stars under the null hypothesis, and also I return the standard error for beta hat. So let's actually run this. This is on page 640 then. So what we get here is exactly what we basically observed before. So we're just working with the observed data. But look at this. Here's beta hat 0, beta hat 1 minus 1. Hopefully that makes sense. Because we have adjusted our response to be basically minus y minus 1 times x. That's why we get beta hat 1 minus 1. And we get the same standard error as what we would before. Why? Well, of course, a simple shift of all your data values, it doesn't affect the variance. So then I do the bootstrap. Chose 999 resamples to be consistent with the book. I really prefer to use a large number of resamples. That's just what they did. The key thing to realize here is I use the strata argument, so I can do my stratified resampling. And here's my output. Okay. The bottom page 40 there, I just, I did this in Chapter 3 as well. I just, take a look at all the actual, for the first resample, I look at the actual indices that were actually resampled, just to show you that indeed the first 60 are always between 1 and 60, and the last 60 are always between 61 and 120. And this is a verification. Okay. This is where you need to be careful. Let's find Z0 itself. I'm going to find Z0. So take beta, you would take beta hat 1 minus a hypothesized value divided by the square root of the estimated variance of beta hat 1. That's how you would think you would do it. But we don't do that here. The reason being is because we are actually working with this adjusted data. So instead of, let's say, having beta hat 1 there, sorry for my notation here, how about beta hat tilde 1 minus 0, because with the adjusted data, now we've transformed this to a hypothesis test where we're working with a hypothesized value of 0 divided by, again, square root the estimated variance.
Can you say that again?
Which part?
So what is the beta hat tilde?
Basically, I'm thinking of it that way.
Okay.
Gosh, I wonder if I could somehow work in a third symbol above that. I'll think about it. Anyway, so so what I do is I actually pull out my beta hat 1 tilde, let's say, for my boot.res object, subtract off 0, divide by then the corresponding standard error. That's my z zeros now. And then my z star 0, that's what I do. As you would expect, beta hat star tilde minus 0 divided by the corresponding standard error. I find my p-value. Remember, it's a one-sided test, so it's a right-sided test. So that's why I have a greater than or equal to there, and I get a p-value of 0.277. This is very similar to the p-values that the book got. It did the test like how I did it, and also did the test where you don't have to resample the null hypothesis. Well, let's actually look at now the distribution of these z star zeros. Again, you would hope that they are close to a standard normal. If everything worked out here, you expect them to be standard normal in terms of the underlying assumptions of your model. So here's, using the usual kind of code, here's a histogram. I put a normal distribution, I fit a normal distribution to the histogram. The green bar represents Z0. And also I do an EDF of the Z stars. And you can see that normality seems to hold. Note though, and perhaps I should have done this, note though I did not use a standard normal on both these plots. Why would I think of standard normal? Because again, normally we would use a t-distribution, which for a sample size such as 60 here would give us a standard normal. Perhaps I should have used a standard normal. I didn't. I just used the mean of my z star zeros and the variance of the z star zeros, and I fit a normal distribution to it. So as you can see, we get kind of the results that we would hope for. And so you might be thinking, well, why are we doing the bootstrap here then? Well, think of a particular case where maybe some of the assumptions would, we had possible violations of our model of assumptions. It wasn't necessarily strong evidence, but I would expect if we had stronger evidence of violations of the model assumptions, we would see more differences between this and using the usual tests. And let's just remember what the usual tests would give us. It gave us a p-value of 0.282, very similar to our p-value of 0.277. And also another reason why we use the bootstrap here is, again, as kind of a theme for this class, is I try to use the bootstrap, demonstrate in settings that are similar to other settings that you've seen, as kind of a way to, kind of as a check to make sure what the bootstrap's doing is correct, because you would have got the same answer using the normal methods. And so that then after you get done with this class, then you have a general sense of how to apply the bootstrap. Now you can apply it to maybe your non-standard problems that you might be faced with in your research. On your own, you can investigate how to do the test for beta 1 is equal to 0 versus beta 1 is not equal to 0. Wouldn't be of interest in this case, but if you did want to do it, I actually show you the code in my program. Okay.
Real quick, just to make sure I'm understanding it right. When you use a subscript of 0, like Z0 star or like beta 1 comma 0, that's to indicate that it's under the null hypothesis, right? Okay.
Any other questions? Okay. And that's it for today. Have a good Thanksgiving.